Hi folks, Mr. Long here. Just going to go over the solution set for the mastery questions on the rational functions and limits test. So let's go through the first one of the mastery, 1A, and we're asked to do the limit of x squared minus 100 over x minus 10 as x approaches 10. Now the first thing we always have to do with these types of questions is determine if it's an indeterminate limit. So in fact, is this one indeterminate? So let's see here. I've got to replace that x right there with 10. So 10 squared is 100 minus 100 is 0. And then I've got this x. I've got to subtract 10 from it, and I also get 0. So that, in fact, yes, that's an indeterminate limit. So 0 over 0. So that means that a 0 over 0 limit, which is indeterminate, it means that there's probably some sort of factoring that I can do in that question. And you can see right away in the next step right here that yes, there was some factoring that we could do. We can factor x squared minus 100 as a difference of squares to get x minus 10, x plus 10, and then divide that by x minus 10, which is in the denominator. And then does that remove our 0 over 0? Because 10 minus 10 is 0, 10 minus 10 is 0. So we've removed our indeterminate relationship, okay, the 0 over 0. Now instead of just approaching 10, because the reason why I couldn't get to 10 before is because I had 0 in the denominator. So I've removed the 0 over 0. Now I can actually, instead of just approaching 10, I can get to 10. So I have x plus 10. Now I can let x equal 10. So this x right here becomes 10. So I have 10 plus 10, which works out to 20. And you didn't have to say this part of it here. However, it's good for you to understand that in fact that's a point discontinuity at 10, 20, and the limit value is 20. Part B, square root form, or square root, a radical in a limit. Again, first thing we should always check is see if it's indeterminate. And I'm approaching 16 in this limit. X is approaching 16, and I have root x minus 4. So that's root of 16 minus 4 over 16 minus 16. Oh, so that is definitely a 0 over 0 limit. And I didn't leave room for that because I was worried about not having enough room in this one because I'm going to do two methods. But yes, it is 0 over 0. It's indeterminate. So again, it probably means I need some factoring strategies of some sort. And I can figure out what the limit is. So what we're going to do here is we are going to go across. Actually, let me bring out just a box here to bring across there so we can focus on one thing at a time. Okay, so I have this limit here that I need to do. Now, what I noticed was I had root x minus 4, and it's hard to see that as a difference of squares, the x minus 16, but if I look, what's the square root of 4? Or square root of 16, rather, is 4. What's the square root of x? Root x. So in fact, what I've got here, x minus 16 can be represented as a difference of squares. Root x minus 4, root x plus 4, which I did. I factored that. What's significant about that is that I have root x minus 4 in the numerator. So this is, in fact, the bottom can be represented as a difference of squares. And I look at x minus 16, I look at root x minus 4, and I recognize that pattern. What's the purpose of that? Well, it's an indeterminate limit. Does that eliminate the indeterminate part? Well, let's see if it does. So root x minus 4 is a common factor with root x minus 4, and that's what generates 0 over 0. So once I remove that, the only thing I have left is root x plus 4 in the denominator. I no longer have 0 over 0, and I don't have to get close to 16. I can actually reach 16. So I wrote it once more as limit as x approaches 16, root x plus 4. But now I'm actually going to let x be worth 4 because I can get to 4. So that means that I can replace x with exactly 4. And I have, or sorry, x equals 4. X does not equal 4, folks. X equals 16. And so that should be root of 16 there. Whoops. We're going to pretend that that's a 16. Okay, so that's root of 16 plus 4. Well, the root of 16 is 4. 4 plus 4 is 8, so that's 1/8. Okay, the reason x equals 16 is because we were trying to figure out the limit when x equals 16. Okay, so it's 1/8. Now that's a factoring strategy, but we can also use a rationalizing strategy. And the factoring strategy doesn't always work when you have radicals. It's only in specific cases where you see very clearly that it's usually a difference of squares like this. More often than not, you'll have to use what's called a rationalizing strategy. And the rationalizing strategy is what's going to be shown here. So again, let's start with the same limit. And when we rationalize, we remove radicals by creating a difference of squares. We don't factor to get a difference of squares initially, we create a difference of squares. So I have to rationalize with the part that with the square root. So what I do is I multiply by the conjugate pair. Conjugate pair means the same terms but opposite sign. Remember, terms are separated by plus and minus signs. So I've got root x minus 4, therefore the conjugate pair to root x minus 4 is root x plus 4. But I can't just multiply by root x plus 4 on the top. That would change the equality of that limit. But if I multiply the top and the bottom by the same thing, in effect I'm multiplying by 1. So let's take a look at that and see what happens. So there's my original limit there, and now look at this. I'm going to multiply the top and the bottom by root x plus 4. Now there's something nice here. Root x minus 4, root x plus 4. What does that work out to? Well, it's a difference of squares. It's going to become root x times root x. What's root x times root x? X. Negative 4 times positive 4, negative 16. So I've got x minus 16 because that's a difference of squares. So now I've got x minus 16 in the top, x minus 16 in the bottom, and root x plus 4. So in fact now I can eliminate those two factors that cause 0 divided by 0, and I'm left with root x plus 4 in the bottom. Now it's exactly the same as up above. It's no different, except this time I got it right and put x equals 16. So I have, whoops. So I have 1 over root 16 plus 4, which is going to work out to 1 over 8. Okay, so again, two different strategies. Either one is acceptable. In terms of going forward for next year, you definitely want to know the rationalizing strategy. Okay, let's do a limit at infinity. The last couple are limits at infinity. So this one here is, I'm going to go to the far left. I'm going to negative infinity. And just to reinforce things, when we look at this in terms of what do I notice? Well, I notice in the top the biggest exponent is x cubed. I notice in the bottom the biggest exponent is x cubed. So really, what's significant here? 3x cubed is significant and x cubed is significant because 2x at x equals even 100 is much, much smaller, 2 times 100, and then 3 times by 10 cubed, which is 1,000, right? So that would be at x equals 10, rather. Even at x equals 10, 2x is tiny compared to 3x cubed, right? Think about that. 2 times 10 is 20. 3 times by x cubed, that's 1,000. It's 20 versus 3,000. So even at 10, well, you can imagine as you go out to 10, 100, 1,000, 10,000, a million, a billion, a trillion, and so on. That this 3x cubed is really the only significant value in the numerator, and then the bottom, the only significant thing is x cubed. So we know from the work that we've done earlier that in the end, it's just that's going to be insignificant, that's insignificant, and that's insignificant. So we know our answer is going to be 3. The question now is, well, how do we actually show it algebraically and prove it? So what I'm going to do is factor x cubed out of so I take the highest exponent in the denominator and factor that out. So I'm factoring x cubed out of the bottom. So x cubed factored out of x cubed is 1. Remember, factoring is dividing. Then I factor x cubed out of x. So I have 2 over, that should be x squared. And then it's going to be minus 1 over x cubed. Okay, that's what I have here. Then in the top, again, I factor x cubed. Whatever I factor out of the denominator, I have to factor out of the numerator. Otherwise, I've lost my equality. So again, remember, factoring is like dividing, right? So if we divide the same thing out of the top and the bottom, it's like dividing by 1. So I'm factoring x cubed out of the top. X cubed out of 2x is 2 over x squared. X cubed out of 3x cubed, factored out, is just this 3 here. So now x cubed divided by x cubed is 1. How big is 2? Oh, that's actually the next line's work. So if we go down to the next line, we can see that the x cubes divided by x cubed is 1. 2 over infinity, negative infinity squared. Well, that's basically 0. 2 over x, 2 divided by negative infinity, again, 0. 1 over negative infinity cubed, 1 over a billion, billion, billion is 0. So what do we have left? Well, not much. We've got 3 left in the numerator, 1 left in the denominator, and that equals 3. So that would mean we have a horizontal asymptote at y equals 3. Okay, at y equals 3. Okay, so big idea there is we can see intuitively what the answer is without doing calculations, significant calculations. However, we do this factoring to really prove, like, it's one thing to say that 2x is insignificant to 3x squared. It's quite another thing to say 2 over x squared is 0, right? And I get it. I used to always do it this way, just by reasoning. But now that I think about it more, I understand that the formality that you really need here to say 2 over x squared definitely approaches 0 as x goes to infinity. Okay, so let's try our last one, which is going to have some absolute values in it. So here we're doing the limit, and we see that, what do I notice here? I notice there's a square root. I notice there's a square root, and I also notice the x squared under the square root. That tells me that there's likely to be some absolute value involved. And that's important. And I also notice we're going towards negative infinity, which is far to the left. So again, the strategy is no different than what we did previously. We factor the greatest exponent out of the denominator. Now, here's my question to you. I've got an x squared, but it's under a root sign. So what's that equivalent to? Well, let's think about this. If I have a 3 outside, just go over to here. If I have a 3 outside a square root, what do I have to do to the 3 inside to make it equal? Well, I have to write 3 squared. Oops, that's not much of a 2, is it? We're going to pretend that's a 2. So if I want 3 squared is 9, right? Square root of 9 is 3. So a 3 outside a square root is the same as 3 squared inside. So since I need to factor an x squared out of the bottom, that's like factoring x outside, right? So a square inside a square root is the same as exponent 1 outside the square root. So if I'm going to have to factor x squared inside a square root, that's the same as factoring x outside. So if I'm factoring x outside, that means I have to factor x out of the numerator as well. So I'm factoring x out of the top and x out of the bottom, except that it shows up as an x squared inside the square root sign. So I'm factoring x squared out of 16x squared. That's x squared. I'm factoring x squared out of 3. That's 3 over x squared. Then in the numerator, I have to factor out x. Factoring x out of 8x is 8. Factoring x out of plus 1 is 1 over x. So I can do a few things right away. I can see that 1 over x, 1 over negative infinity, is going to go to 0. I can see that 3 over x squared, 3 over negative infinity squared, that will also be 0. So all I'm left with is the x, the 8, the x squared, and the 16 under the square root sign. Now, and I've simplified that here, right here in the next line. Now, what is that worth? What do we recognize that as, square root of x squared? Well, the square root of x squared is nothing more than the absolute value of x. Okay, absolute value of x. And so since it's the absolute value of x, we need to start considering what happens on either side of 0. Right? So if I'm at the y-axis, where x equals 0, on the left side, the curve y equals, or the line y equals x is negative x, but on the right side, it's positive x. Well, we're approaching negative infinity. So since I'm approaching negative infinity, I'm way over here on the left side. So what's the equation of the curve way on the left side? Negative x. So what I'm going to do is I have this x, and then I replace square root of x squared with negative x. Right? That's negative x. Square root of 16, by the way, is 4. So x divided by negative x is negative 1. 8 divided by 4 is 2. So it's the negative of 2. Negative 2. Okay, so that means it's a horizontal asymptote at y equals negative 2 going to the left. Okay, folks, so those are all your limit questions in question 1. Make sure you go over them carefully. If you have any of them that you need to redo for your mastery.